If, in some cataclysm, all of scientific knowledge were to be destroyed and only one sentence passed on to the next generation of creatures, what statement would contain the most information in the fewest words? I believe it is the atomic hypothesis, or the atomic fact, or whatever you wish to call it, that all things are made of atoms. 5, 4, 3, 2, 1. The ship rattles as it stretches out into the void, beginning the adventure of a lifetime. The nervous crew are off on an epic journey to visit their homeworld's only natural satellite. Though similar in concept to the journey undertaken by the Apollo astronauts when they left Earth for the Moon, this voyage is very different. When Armstrong and Aldrin headed for history on the lunar surface, they needed only to travel a distance equal to the width of 30 Earths. Our intrepid travelers must cover a distance equal to more than 63,000 times the diameter of their home world. Compared to this crew's destination, though, the Moon is a celestial snail. It crawls around the Earth once a month at a speed of 1,000 meters per second. That may sound fast, but this satellite is whipping around at over 2 million meters per second, or just under 1% of the speed of light. It's moving so quickly that it completes 6.5 quadrillion orbits each and every second. For it is no moon. And this is no solar system. Our travelers are not exploring the astronomical realm, but the atomic one. They are brave atomonauts adrift inside the hydrogen atom. Departing from the solitary proton at its center, they are in search of the lone electron that encircles it. But their mission is even harder than it first appears. For the electron only orbits the proton like a moon orbits a planet in the simplified Bohr model of the atom, named after the Danish physicist Niels Bohr. Modern quantum physics say that we can never know for certain where the electron actually is. We can only say where it's most likely to be. The blur of all its possible paths creates a cloud around the nucleus. Our atomonauts could therefore never land at their destination, only float into the fog of possibility. Today, these bizarre atoms are the universe's Lego bricks. Vast galaxies swirl in the void and distant stars keep vigil over the night, but they are all built out of atoms, as we all are. Indeed, there's an entire cosmos inside you. The number of atoms in your body alone exceeds the total number of stars in the entire observable universe. Even if you started counting them at a rate of 1 billion a second, it would still take you far longer than the current age of the universe to complete the task. And as we have already seen, even within the atoms themselves, there are entire complex systems to explore. And yet, at the very beginning of time, the number of atoms in the universe was precisely 0. Not a single atom in the entirety of the cosmos. So how did we end up here? Where did the very first atom come from? And just why is everything made of atoms? The Earth weighs about 6.58 billion trillion tons, and about 1.85 billion of that is carbon. The climate can sometimes feel like an impossibly big problem for one person to try and solve. And that is where Wren comes in, our sponsor today. Wren is a website where you can calculate your carbon footprint, then offset it by funding a mix of carbon reduction projects, like tree planting, mineral weathering, and rainforest protection. By answering a few simple questions about your lifestyle, you can find out your carbon footprint and how to reduce it, and then you can actually offset what you have left over. You also receive regular updates on what you support. One particularly impressive project is biochar in California, which prevents wildfires by removing dead and flammable trees, then turning the biomass into biochar, thus stopping it from ending up in the atmosphere. A cutting-edge way to tackle the climate. So, offset your carbon footprint on Wren. The first 100 people who sign up using the link in the description will have 10 extra trees planted in their name. Thanks to Ren for supporting educational content on YouTube. A wicked wind howls across the Black Sea. Waves swell and crash as the previously mirror-smooth water is tossed and churned. Marooned on a kayak amid this maelstrom is a pair of newlyweds. They are refugees fleeing Ukraine to escape from the Russian regime. Yet this is not a 21st century story. The year is 1932, and the couple stranded in the tumult are the physicist George Gamow and his wife Lyubov, who he affectionately calls Ro after the Greek letter. But what could have driven this young couple to risk their lives on such a perilous journey? The early 1930s witnessed a big shift in the way the Soviets treated their scientists, and intellectual ideas and foreign trips were increasingly tightly policed. Gamow wants to present his research at a large scientific conference in Rome, but needs a new passport. His application is constantly kicked into the long grass by bureaucrats in Leningrad who promise progress but instead deliberately run down the clock. He never goes to the Italian capital. Yet his endless visits to the passport office have one significant upside. It is there that he meets Ro. They marry soon after, and within a year the newlyweds agree to flee. They pore over maps looking for the surest means of escape from the Soviet Union, and so they settle on the Black Sea, leaving Gamow's birthplace of Odessa to head for Turkey. Gamow still has a Danish motorcycle license from his days collaborating with the physicist Niels Bohr in Copenhagen, and so the plan is to wash up on a Turkish beach, pretend to be Danish, and ask to be taken to the Danish embassy in Istanbul. Their journey couldn't have started better. The water is calm and the breeze is gentle, but when they awake before sunrise the second day, the weather is already turning. By the evening, the situation intensifies and soon becomes perilous. By the time the storm abates, they are exhausted to the point of hallucination. Drifting alone on the open water, strong winds buffet the boat all the way back to Crimea. Despite this setback, eventually Gamow and Ro do escape. They secure passage to a scientific conference in Belgium, and after the conference, Marie Curie helps the couple extend their stay in Western Europe. Never to return to the Soviet Union, they finally headed to the United States in early 1934. This entire odyssey has unfolded before Gamow's 30th birthday. 6 years later, Gamow is granted American citizenship. Free from the shackles of oppression, he is now able to continue his work. And it is this work that would turn out to be pivotal in our understanding of physics, for it would change the way we think about the history of the universe forever. In 1929, 3 years before Gamow's exploits on the Black Sea, the American astronomer Edwin Hubble had shocked the astronomical establishment with evidence that the universe is expanding. If the universe is growing day by day, then it was smaller yesterday and smaller still a week ago. Keep rewinding the clock, and there was a time when every part of the modern universe was concentrated down into an incredibly small space before it expanded outwards. The Big Bang. Except that it wasn't such a new idea to Gamow. The Russian physicist Alexander Friedmann had already predicted the universe's expansion back in 1925, and the pair had had lengthy discussions about it during Gamow's time in Leningrad. Gamow was spending much of his early time in America working on something else, the ultimate power source of stars. Yet the focus of his attention was shifting, and in October of 1945, Gamow writes a letter to his old friend Niels Bohr to mark the Dane's 60th birthday. The letter reveals that Gamow was starting to apply his work on the internal mechanics of stars to the origin of matter in the early universe immediately after the Big Bang. Up until this point, cosmologists had assumed that the early universe was dominated by matter, the stuff that all visible structure is made from stars and planets to galaxies and galaxy clusters. Yet Gamow began to suspect otherwise. History wavers on who truly deserves the credit, but it could have been Gamow's student Ralph Alpha. In his doctoral dissertation, Alpha claimed that the early universe wasn't dominated by matter, but by electromagnetic radiation. This electromagnetic radiation would supposedly dominate the early universe for a full 50,000 years after the Big Bang. physicists have another word for electromagnetic radiation: light. We may use that word for the light our eyes can see, but there's more to it than that. Just as there are frequencies of sound too low or too high for our ears to hear, there are frequencies of light too low or too high for us to see. When a physicist uses the word light, they mean the radiation that spans the full range of these frequencies, from gamma rays and X-rays at the high frequency end to microwaves and radio waves at the other. When you use a microwave to heat your dinner, you're actually cooking the food using low-frequency light. And so, light and matter were trapped together in this nascent universe. After 100,000 seconds of expansion, the entire universe was still denser than the air you're breathing right now, and continued for thousands of years to be dense enough for sound waves to travel through. Sound waves of such low frequency that they'd need to be squashed 100 septillion times, that's 1 followed by 26 zeros, just to push them into the range of human hearing. Something that, in 2013, John G. Kramer at Washington University used data from the early universe to reproduce. Cosmologists call these sound waves baryon acoustic oscillations, and they can still be detected today using facilities such as the Sloan Digital Sky Survey. As the universe kept expanding, it continued to stretch out these sound waves, shifting them to ever lower frequencies. But then came a point when everything changed. It is one of the most important events in the entire history of the universe, and it was predicted by none other than Alpha and Gamow. It is called recombination, and it also opened the floodgates for the very first light to come streaming out into the early universe. But what recombined exactly? And what does this first light have to do with the first atom? The feeling of claustrophobia rises by the second. You're trapped. Whichever way you turn just leads to a blocked path. Have you seen these walls before? Did you turn left or right at this junction earlier? No matter how hard you try, you just can't figure out how to escape. And that is not surprising, because there is no escape. You are trapped in an impenetrable maze. This series of never-ending dead ends is exactly what light encountered after the Big Bang. Everywhere light tried to go, it bumped into insurmountable obstacles in the form of subatomic particles. And yet the universe didn't begin as such a labyrinth. In the very beginning, there was none of this matter to get in the way. For the faintest sliver of a second, just after its birth, it was free. However, very quickly light turned into its own captor, snapping the shackles shut on itself. This happened because light leads a double life. Like the vampires and werewolves of myth and folklore, it can shapeshift into something else. Matter. Light is a form of energy, and energy and matter are two sides of the same cosmic coin. And the more energetic the light, the higher the likelihood that it will change into matter. And so, within a trillionth of a second after the Big Bang, some of the universe's energy is converted into particles of matter that start popping into existence, flooding the universe with fundamental particles, everything needed to build atoms, including electrons. Yet we'll still have to wait hundreds of thousands of years for these particles to actually coalesce into the first atom. We may already have electrons, but to make a hydrogen atom, like the one explored by our atomonauts, we also need a proton. Unlike electrons, they are built out of something else. Quarks, fundamental particles that also appeared during light's partial metamorphosis into matter. Quarks come in a menu of different flavors, but the most important ones for our story of atom formation are the up quark and the down quark. Up quarks carry a positive charge and down quarks a negative charge. A proton is made of 2 up quarks and 1 down quark, giving a proton an overall positive charge. Yet these quarks are not natural bedfellows. Electric charges act like the poles of a magnet. Opposites attract, but like charges repel one another. And so how can 2 positively charged up quarks happily sit side by side inside a proton. The solution to this puzzle lies with forces, the glue needed to stick the first atom together. Physicists know of 4 fundamental forces in the universe. 2 are familiar to us: gravity and electromagnetism. Light is an electromagnetic wave, and it is electromagnetism that repels the magnets and quarks from one another. But down in the atomic world, 2 less familiar forces are at play. The weak nuclear force governs radioactivity, but it's the strong nuclear force that really dominates here. It is 1 duodecillion times stronger than gravity. That's 10 followed by 38 zeros, significantly more zeros than there are stars in the entire observable universe. The strong nuclear force is also 100 times stronger than the electromagnetic force. So 2 quarks with the same charge may want to push away from one another, but the strong nuclear force can override this electromagnetic instinct and keep them tied together. There is a catch, though. The strong nuclear force may be the king of the forces, but the kingdom it governs is tiny. It only has dominion over the most minute of distances, about a trillionth of a millimeter. Initially, energies are too high for quarks to bind together through the strong force. When the quarks first formed, the temperature of the universe was over 1 quadrillion degrees. Though they pass very close to each other, the quarks collide with such high energy that they cannot stick. But this new universe is expanding all the time. It cools as it grows, and particles within it slow down. After the first millionth of a second, the temperature drops to a mere 1 trillion degrees, and the first protons are able to form. Neutrons form too, the other kind of particle you'll find in an atomic nucleus. They are made up of 1 up quark and 2 down quarks. Simple enough, you might think. But again, as with Bohr's model of the atom, neutrons and protons are not quite that straightforward. Indeed, the more physicists learn about the proton, the more downright weird it gets. To quote Mike Williams, physicist at the Massachusetts Institute of Technology, "This is the most complicated thing that you could possibly imagine." For one thing, together, the 3 quarks, known as valence quarks, actually make up just 1% of the proton's mass. The rest is taken up by particles called gluons. They are the particles that carry the strong nuclear force, and it's by exchanging gluons that the trio of valence quarks are able to bind together into a proton. Yet it gets a lot stranger. Occasionally, gluons pick up enough energy that they can do some shape-shifting of their own, turning into a quark and its antimatter equivalent, the antiquark. These so-called C-quarks then quickly recombine back into a gluon. So at any one time, a proton is really a blur of valence quarks, gluons, and C-quarks. We still don't understand all the details, and experiments like the relativistic Heavy Ion Collider in New York are helping physicists probe deeper. What we do know is that gluons and C-quarks make up 99% of the proton's mass. Because they aren't permanent, physicists refer to the C-quarks as virtual particles. This means that the mass of the proton, the particle you'll find at the center of every atom in the universe, mostly comes from an infinity of C-quarks that don't actually exist. From top to bottom, strange to charm, a whole range of quarks can be found as C-quarks, popping in and out of existence for just short enough periods to not break conservation of energy. A recent experiment at the University of Milan has even shown that sometimes charm quarks actually appear at lower energies, and most bizarrely of all, charm quarks have almost 1.5 times the mass of the entire proton, the low probability of them appearing meaning that their full mass isn't added to the proton itself. The quantum world of the very small is a counterintuitive place. Returning to the universe's timeline, now that we have protons and neutrons, the next step on our journey to the first atom comes as the universe continues to cool and expand, meaning the protons and neutrons lose speed. And it is here that George Gamow re-enters our story. In 1948, he has a letter published in the scientific journal Physical Review Letters. It runs to no more than a page, but its length belies the magnitude of its insights. The paper suggests that within a handful of minutes of the Big Bang, the universe cooled to 1 billion degrees, enough to allow the strong nuclear force to stick a proton to a neutron. This proton-neutron pair is known as a deuteron, and it's the gateway to a whole new way of building structure in the infant universe. Stars like the Sun generate vast amounts of light by churning hydrogen into helium through a process called nuclear fusion. Slightly less helium comes out than the amount of hydrogen that goes in, and the difference is converted into sunshine as mass turns back into energy. Along with Ralph Alpha, Gamow was the first to figure out the series of steps by which fusion turns hydrogen into helium, and deuterons played a crucial role, for when a deuteron combines with a proton, it makes the nucleus of a helium-3 atom. Then, when two helium-3 nuclei fuse, they make the nucleus of a helium-4 atom and 2 extra neutrons. In the modern universe, these reactions can only unfold in places with extremes of temperature and pressure, like the cores of stars. But similar temperatures were present universe-wide soon after the Big Bang, though not for long. There was only an incredibly short window of opportunity for fusion to take place. The temperature had to be cool enough for deuterons to form in the first place, but still hot enough to fuse everything else together. And that window opened less than a second after the Big Bang and slammed shut about 20 minutes later, when the temperature of the universe cooled. A roughly 20-minute period in which about a quarter of the universe's mass of hydrogen nuclei turned into helium nuclei. And so, we have a universe that's still just 20 minutes old, sprinkled with 12 hydrogen nuclei for every 1 helium nucleus and 1 billion particles of light for every nucleus. Impressive progress for just over a quarter of an hour. But we still didn't have the first atom. For that, we need to bind electrons in orbit around these nuclei. And that would take a very long time indeed. Electrons are negatively charged, and protons make atomic nuclei positively charged. Opposites attract, and so the electromagnetic force can snare a passing electron and trap it in orbit around the nucleus. But the electromagnetic force is 100 times weaker than the strong nuclear force, so the universe has to cool all the way down to just 4,000 degrees in order for the particles to slow down enough for the electromagnetic force to do its thing. This will take 380,000 years of expansion, and only then, finally, the first atom forms. But, as with the bizarre components of its nucleus, adding electrons certainly doesn't make things any less complicated. Electrons were discovered towards the end of the 19th century, yet time has only burnished their enigma. At almost 2,000 times lighter than a proton, an electron is generally thought to be a single point with no shape or internal structure, truly fundamental, like quarks. They don't orbit the nucleus like planets around the sun either. Quantum physics tells us that it is impossible to know both the position and speed of an electron with perfect accuracy. At any one time, an electron isn't just in one spot around the nucleus, it simultaneously occupies every possible spot. One single electron envelops the nucleus like a fog, and we can only talk about where it is most likely to be. Electrons, as with all other fundamental particles, also have a curious property called spin. They are deflected by magnetic fields as if they were rotating balls of charge. But this rotation is counterintuitive. If you spin around 360 degrees, in other words rotate through a full circle, then you'd return to where you'd started. You're a spin 1 entity. But electrons are spin half entities. They have to be rotated 720 degrees to return to where they started. Except that electrons aren't actually spinning at all. Quantum physics forbids it. Though it is useful to think about them as spinning, they can't be. And so, everywhere we look, the inside of an atom is like a giant hall of mirrors. Deception, illusion, and subterfuge accompany each of our endeavors to understand it, a bizarre quantum realm that runs counter to common sense, wrapped up in mysteries that we are very far from unraveling. But what we do know is that the formation of the first atoms some 380,000 years after the Big Bang set light free. Photons of light now have a way out of the previously impenetrable maze that they had inflicted upon themselves. With electrons suddenly sucked into orbits around atomic nuclei, there is an abrupt increase in the space between matter. Light can travel without whacking into anything, and off it goes at 299,792,458 meters per second. In 1948, Ralph Alpher and Robert Herman built on this work and predicted that this first light to flood out into the universe hundreds of millennia after the Big Bang should still be visible today, and finding it would be the equivalent of a smoking gun, a hard-to-argue with proof that the universe really did begin with a hot Big Bang. Unfortunately, no one took much notice, and the idea was largely forgotten for a decade and a half. Until a fresh-faced Robert Dicke stands on the roof of the radiation laboratory at the Massachusetts Institute of Technology, holding a device of his own making, aloft. Dicke joined MIT under a cloak of secrecy in September 1941, having only just completed his PhD at the age of 25. The Second World War has been raging for 2 years, and although the United States remains neutral, it is starting to make preparations for joining the fray. They were right to. Within weeks of Dicke starting at MIT, the Japanese attack Pearl Harbor, and the United States enters the war the very next day. Dicke is a keen inventor with a real skill for electronics. It's in the blood. His father was a patent attorney, and Dicke Jr. would go on to file over 50 patents in his lifetime for devices from clothes dryers to lasers. But at MIT, Dicke is working on radar. The term radar, an acronym for radio detection and ranging, was coined by the US Navy just years before. By sending out short pulses of radio waves, you can detect objects like enemy aircraft when they reflect those radio waves back to you. Except that radar was initially a pretty blunt instrument. Radio waves are a form of light, part of the electromagnetic spectrum. They have the longest wavelength of any light, the distance over which the wave repeats itself. Radar has been around since the 1930s, but Dicke is working on a big improvement, using microwaves instead. Microwaves have a shorter wavelength than radio waves, meaning your radar picture will show greater detail. Dicke invents a new receiver to pick up these reflected microwaves, now called the Dicke radiometer. Yet the curious child within him can't help but look even further up, beyond the bombers and the dogfighters, to space. Dicke wonders whether any microwaves are coming from the cosmos. And so here he is, on the roof of the radiation laboratory of MIT, pointing his radiometer to the sky. It's an idea he would return to over a decade later at Princeton as part of one of the most important insights in 20th century cosmology. Ultimately, it would validate our story of the origin of the very first atoms. As with many of us, Dicke found the idea of the Big Bang a little conceptually troubling. How can something come from nothing is perhaps the most asked question about the universe's origin. So Dicke explores the idea of cyclical universes, an expanding universe that slows, stops, and shrinks, collapsing back in on itself in a big crunch, only to explode outwards again in another Big Bang. A collapsing universe would get exceptionally hot as matter crushed down on itself. Electrons would get ripped away from protons as the universe returned to a sea of subatomic shrapnel. Dicke dubs this mega-hot maelstrom a fireball. The ensuing bounce and expansion would cool the fireball back down and allow atoms to reform, and this is where the name recombination originates. In this theory, the atoms truly would recombine. By thinking this scenario through, Dicke, like Gamow over a decade earlier, hits upon the notion that there should be some relic radiation left over from this superhot stage, and that it would still be visible today. He calls it fireball radiation, and it's the same radiation from recombination that Gamow and his colleagues predicted back in 1948, although Dicke is initially unaware of their work. Dickey reasons that this fireball radiation should now be in the microwave part of the electromagnetic spectrum, the very part he has spent 2 decades working on. Of course, initially, the leftover light from the Big Bang would have been in the visible part of the spectrum. Had anyone been around to see it, it would have glowed yellow-orange. But the universe has continued to expand ever since the light was released 13.8 billion years ago. That expansion has stretched the space between everything, also redshifting any waves of electromagnetic radiation traveling through that space. Dickey calculates that this fireball radiation would have been stretched right out through the infrared and into the microwave spectrum. And so he resolves to find it with his eponymous radiometer and begins to plan an observation run that would start in the mid-1960s. But something strange happens before he has a chance to finish his work. 45 minutes drive away in Homedale, New Jersey, 2 radio astronomers are attempting a different kind of experiment. Their names are Arno Penzias and Robert Wilson. Like Gamow before him, Penzias fled European totalitarianism, a child evacuee from Nazi Germany. Penzias and Wilson are using the giant 6-meter Homedale horn antenna, part of Bell Telephone Laboratories, to listen out for radio waves reflected off orbiting satellites. The signals they are looking for are very faint. To hear them, they must first get rid of any other interference. They eliminate local radar and radio transmission and even remove interference from the receiver itself by cooling it to -269 degrees Celsius using liquid helium. Yet despite their best efforts, there remains an annoying hiss in the detector, like the static between channels on an old radio. Where could it be coming from? It seems to be coming from all over the sky. And it is then they spot what must be the culprit. Penzias and Wilson discover pigeons roosting in the antenna. The heat from their droppings, what they would later call a white dielectric material, must be creating the noise. The pigeons are carefully trapped and sent to the town of Whippany, 30 miles away, only for them to fly right back. In the end, they sadly meet their demise. Penzias and Wilson meticulously clean out their droppings. But the hissing remains. In all, Penzias and Wilson spend over a year trying to figure out the source of this maddening interference. Desperate, Penzias starts phoning round, asking others if they have any idea what's going on. Dickey is in his office, in the middle of a meeting about building his device to look for fireball radiation. As soon as he hears what Penzias has to say, his heart sinks, and he says to his colleagues, "Well, boys, we've been scooped." Penzias and Wilson pick up the 1978 Nobel Prize in Physics for their serendipity, and Dickey is left empty-handed. Gamow would never win a Nobel either. And so ends the story of the discovery of the cosmic microwave background, the unmistakable fingerprint of the formation of the first atoms, undeniable proof that our universe started with a hot Big Bang. As the earliest light dispatched into the universe, it is an image of an infant cosmos. If our present universe were a 40-year-old human, the cosmic microwave background is the equivalent of a photograph taken when it was less than 10 hours old. Hidden within it are clues to the universe's future, our present. Small temperature variations signal the existence of tiny differences in density in the infant universe. The more matter that falls into these densities, the bigger they get, and in turn, the more matter that falls in. Within a few 100 million years, the first galaxies will form as matter relentlessly clumps together. And along with this, marked across this map of the cosmos, now stretched to almost 500 million light-years in diameter, are the imprints of the sound waves of the early universe, the remains of the baryon acoustic oscillations. Experiments such as the Dark Energy Survey high up in the Chilean Andes have mapped the layout of the modern universe like never before. Vast superclusters of galaxies stretch out among equally gigantic supervoids, which mirror the tiny temperature variations seen in the cosmic microwave background. The seeds of the universe's structure were sown long ago. But you don't need a giant horn antenna to tune into the universe's youth. In fact, an old analog television set will suffice. In our modern digital age, memories are fading of the snow that would settle across the screen as you twiddled between channels. 1% of that static is the cosmic microwave background. The universe began almost 14 billion years ago, but the formation of the first atom was such a monumental moment in its history that echoes of the event remain our invisible companions throughout our lives and will take trillions of years of expansion yet to be stretched out beyond our view. And so, you may be forgiven for thinking that the rise of the atom was inevitable, the final destination of any hot, dense soup of particles, as fundamental to reality as their constituent parts. But that is certainly not the case. In fact, it is quite the opposite. With the blindfold covering your eyes, your other senses are heightened. You hear every click and snap as the guns are loaded, all 24 of them. You are about to be executed by firing squad. The soldiers raise their weapons and aim the barrels squarely at your chest. This is it, you think, and your body braces for its last breath. Then, every single bullet misses. The Canadian philosopher and author John Leslie asks us to imagine a version of this scenario in his 1989 book, Universes. How unlikely it seems that you're still alive. It only needed one shot to hit its target, and yet every single gunman missed. You owe your existence to an incredibly precise and improbable sequence of events. Any deviation from it, and you simply wouldn't be here. The story of our universe and of its atoms is a similar tale. Since its birth 13.8 billion years ago, the universe has gone from having no atoms at all to being full of more atoms than we could possibly count in trillions of lifetimes. The atom is so ubiquitous that we take it for granted. Atoms, after all, are everywhere. And yet the atom is a ludicrously unlikely entity. Like your life in that courtyard, it teeters on a tightrope so fine that any minuscule misstep would see it snuffed out in an instant. Mess with the physics even slightly, and every trace of chemistry and biology would fade away. Imagine that you could operate the universe using a giant control panel, littered with knobs, dials, and switches, each one responsible for some key property of existence, the masses of certain subatomic particles, the strength of the various forces. In this scenario, it wouldn't take much tinkering to destroy atoms entirely. For an atom to be stable, the orbits of its electrons need to be a lot bigger than the size of the nucleus. Otherwise, the electrons risk crashing down on the atomonaut's homeworld of the proton, like a satellite dragged back to Earth in fire and fury. You'd only have to make the electromagnetic force a little bit stronger, and electrons would be pulled in tighter. Weaken it, and electrons could fly off on their own, like stars flung out from a distant galaxy, rendering them forever out of our atomonaut's reach. Or you could weaken the strong nuclear force. Then protons and neutrons wouldn't hug each other so tightly, increasing the size of the nucleus and hastening the electron's demise. A physicist would say that these forces appear finely tuned. The dials have to be in pretty exact locations, otherwise atoms wouldn't exist. And one of the first people to discuss this so-called fine-tuning in detail? None other than Robert Dicke back in 1961. Electron orbits are far from the only aspect of the atom that appear finely tuned. The neutron, for example, is a mere whisker heavier than the proton by about 1/7 of 1%. Physicists know this thanks to increasingly precise experiments. Indeed, in 2021, a pair of researchers from Florida State University measured the deuteron to proton mass ratio to an accuracy of 4.5 parts in a trillion. This small difference in mass between the proton and the neutron is greater than the mass of the electron. And this is key. Were the electron heavier than the difference in mass between its two bulkier cousins, it could be captured by a proton and turned into a neutron. In other words, you can't change the masses of electrons, protons, or neutrons by much either, or again, atoms simply wouldn't exist. Fiddle with the control panel further and you can cause more mayhem. The reason the neutron is heavier than the proton is due to differences in the masses of their quarks. As we saw earlier, a proton is made of 2 up quarks and 1 down quark. 2 downs and 1 up form a neutron. The down quark is ever so slightly more massive than the up quark, so a neutron is heavier than a proton. Yet these masses appear finely tuned as well. If the difference in mass between up and down quark were larger, the entire history of the universe would have been radically different. A down quark would be able to decay into an up quark. If that happened inside a neutron, suddenly the neutron would become a proton. The deuteron, the key marriage of a proton to a neutron, would be annulled. This means no fusion after the Big Bang and a universe that only contains atoms of hydrogen. None of the 117 other types of atom or elements in the periodic table would exist. No oxygen for you to breathe or iron to carry that oxygen around your body. Changing the mass of the quarks isn't the only way to snuff out the deuterons. They only exist because the strong nuclear force can bind a proton to a neutron in the first place. Make that force just 9% weaker and it would be too puny to hold deuterons together. Going the other way, ratcheting up the strong force by just 2% would have even more profound consequences. It would then be strong enough to bind 2 protons together, a form of hydrogen called a diproton. We've never seen one in the real universe, and there have only been tantalizing and unconfirmed reports of one inside experiments, such as the radioactive isotope beam factory in Japan. Had they existed after the Big Bang, they would have rapidly fused into helium, and all hydrogen would have quickly disappeared from the universe. We live in a helium-dominated universe instead of a hydrogen-dominated one. And so, whichever dial, switch, or knob we contemplate on the great control panel of the universe, it is surprisingly easy to eradicate atoms. In other words, all the settings appear to be in exactly the right place to permit atoms, and the things that they are built from. It seems quite the coincidence. It is as baffling to physicists as your survival in front of the firing squad. And so scientists and philosophers have put forward 3 broad ideas to explain the fine-tuning problem. First of all, maybe it's just dumb luck. After all, the settings all have to be somewhere and, although almost impossible, they could have fallen in the right place so as to give rise to the first atom some 380,000 years after the Big Bang. By one account, the odds of this are about 1 in 65 billion trillion. That's roughly the same odds as you selecting the sun when asked to choose randomly from a bag containing all the stars in the observable universe. Many find these odds too extreme to accept and see this apparent fine-tuning as evidence of something or someone with a steady hand on the tiller. In other words, not being an accident, but the deliberate act of manually setting the dials to the right place. This could be some omnipotent deity or a bored advanced civilization who wants to create their own real-life version of The Sims. There is another option, though. Thanks to strands of evidence like the cosmic microwave background, cosmologists are confident that the universe began with something like a Big Bang. But what banged exactly? When trying to answer that question, a tantalizing possibility emerges. The Big Bang is a good theory, but not a perfect one. And some scientists believe the cracks can be papered over and the theory salvaged if there was more than one bang. Perhaps an infinity of bangs, each one giving rise to a new universe. The settings on the control panel of each universe could therefore vary depending on the exact way the universe emerged from the cacophony, and all possible settings would be found across this endlessly large multiverse. So which of these universes are you going to find yourself in? You can't be in ones in which the dials are set so as not to permit atoms, and in turn the stars and planets made from them. You, a giant lump of atoms, can only find yourself in a universe where the strengths of the fundamental forces and the masses of the subatomic particles allow atoms to form. And what a journey those unlikely atoms have been on. Their constituent parts forming within minutes of the Big Bang to coalesce at recombination before hurtling across space, spinning into stars, exploding back into space, pulled into planets, and eventually ending up inside a brain capable of contemplating its place in this vast and intricate universe. You've been watching the entire history of the universe. Don't forget to like and subscribe and leave a comment to tell us what you think. Thanks for watching, and we'll see you next time.